Hi, everyone. It's my great pleasure to be here at this ECCV workshop. I would like to thank all the organizers for inviting me and for putting together this great program. Today, I will be sharing with you some interesting research challenges and opportunities around handling data distributional shift, which is a problem that's close to my heart. I would like to start the talk by showing you this video. This is a model trained on the Berkeley Deep Drive 100K dataset, performing bounding box tracking on the road. Whenever we see videos like this, we make an overly positive impression of how remarkable deep learning models have evolved to be, which are true in a lot of cases. In my research, I encourage researchers and practitioners to look at the other side as well, to take a cautious view at the methods and technologies that we built. Especially be aware of unexpected situations that the model wasn't trained for. And hopefully by the end of the talk, we can see things in a more well-rounded perspective. I know there are many experts in statistics, machine learning, and AI in the audience. So let's think for a second how you would approach building and deploying such a self-driving car model. So to abstract the process a little, we typically start with collecting some training data with corresponding labels. And then we train on our favorite neural network. And here the output typically contains some predefined categories, such as pedestrian, cars, and truck, and so on. And of course, there are thousands of other details to sort through. But let's say you finally reached a model that you think the performance is satisfying and you think it's ready to be deployed. More unexpected trouble would kick in. Why do I say that? Because the classic machine learning assumption is that what model sees in the deployment time is identical to this training data distribution. However, in the real world, these two distributions can be wildly different and lots of unknowns could emerge. And so this is also called the open world setting in contrast to the classic closed world setting. For example, in our recent work, we took this image from the MS COCO dataset and run through this self-driving car model that was just trained on the BDD dataset. And so you can see that the model would produce overconfident predictions for this unknown object, helicopter, as a truck. And keep in mind that this helicopter was never exposed to the model during training time. So in other words, deep networks do not necessarily know what they don't know. And this has raised significant concerns on models' safety and reliability. As you can imagine, algorithms that blindly classify out of distribution samples into one of the known classes can be catastrophic. And ideally, we want the model to be able to flag such scenarios so that human can take better precautions. And believe it or not, this kind of event can also happen in real life. And to give you a concrete example, here I'm quoting this news article from April this year, which reported that a Tesla vehicle crashed into a private jet that's worth of $3.5 million. Fortunately, no one got hurt in this accident, but you can imagine the gravity of this issue. And so this out of distribution detection problem has become very, very important. And so this is going to be the focus of my talk today. So what is out of distribution data, you might ask? Let me first provide a simple view to set up this definition. Let's say we have our training data distribution, which is a mixture of two Gaussians with class label y equals to 1 and -1. And so our in distribution Pn would be the marginal of this joint distribution defined over the input space x times the label space y. And in test time, these orange dots could emerge, which are out of distribution from an unknown class that doesn't belong to either y equals to 1 or -1, and therefore should not be predicted by the model. And to translate this toy data into some high-dimensional images, you can think of cipher 10 on the left-hand side being the in distribution, and SVHN, street view housing number, on the right-hand side being the OOD, which have disjoint labels. Well, you might think that this OOD is way too obvious to us, but I'm going to show you how such an easy setup could trouble the state-of-art neural networks. And later on in this talk, I'll also discuss how we can go beyond such simplified definition. But for now, let's start with the simple view and go from here. And so SVHN is just one of the OOD that the model would encounter in the wild. And there are, of course, many other unknowns on this complex data manifold. And this is a slide from a talk by OpenAI, which I think very nicely illustrates the complexity and nuances of the problem, right? So the right-hand side depicts this manifold that contains all the possible images that one could encounter and generate on the internet, which is in sharp contrast to the left-hand side, which is the task-specific data set. So out-of-distribution detection is a hard problem, and I would like to spend a few slides explaining the why before we get into the how, the solution. So the first challenge is the lack of supervision from unknowns during training time. Typically, the model is trained only on the in-distribution data, in this case, the green and blue dots, using empirical risk minimization. And you can't really anticipate where these orange dots could emerge in advance, because there can be a huge space of unknowns, right? Especially if you extrapolate this to be some high dimensional space. And this problem is further exacerbated by the high capacity neural networks that we're working with nowadays. And in particular, to illustrate this problem, I would like to use this simple example at the bottom of the slide, where we have this in-distribution data that consists of 3 Gaussians, right, colored in gray. And so if you were to train a neural network using the common cross entropy loss, this model would learn this triangular shaped decision boundary, which would almost do a perfect job in terms of classification, distinguishing these 3 clusters. However, what's problematic is when it comes to out-of-distribution detection, because you see that the decision boundary cannot reliably tell apart these 2 types of data. For example, if you look at those red regions, those correspond to data points that are far away from the gray points. However, they would trigger the model to produce very high output, which causes trouble for OOD detection. You might also be wondering, well, can we perform density estimation to directly estimate P of X using deep generative models? There has been active research along this line as well. However, there are challenges there in the solution space. For example, deep generative models can be difficult to train and optimize, especially for a large-scale data set. And moreover, they don't provide classification ability, which is something that we might be interested in. One last challenge is that real-world images are composed of numerous objects and components, like shown in this picture, right? And therefore, we need finer-grained understanding of this out-of-distribution at the object level, beyond image level. And over the years, we have seen a surge of interest in this challenging problem space. And really, it's great to see a thriving literature on OOD detection. And very recently, my co-authors and I have composed a comprehensive survey that covers the methodologies developed in this space. And in this talk, I'll try to unpack some of these. So the earliest work adopted this post-hoc approach for out-of-distribution detection. And so a model is typically trained on the in-distribution data, say cipher 10, using empirical risk minimization. And once the model is trained, now let's take the network as it is without modifying its parameters. And so during inference time, for any given input, we're going to devise a scoring function S for OOD detection. Essentially, we're performing a level set estimation. If it's below certain threshold, we're going to reject this input. And otherwise, we'll produce the class prediction as usual. And so the advantage of post-hoc OOD detection is that it doesn't interfere with our original task or model that's already been deployed, especially when it's hard to be replaced or retrained immediately. And so in this case, the model is guaranteed to have the same performance in terms of classification while having an additional safety layer almost for free. And so this problem is also different from anomaly detection, which is a classic problem in machine learning that often treat all the data as one class without necessarily differentiating the class labels. And so in our problem formulation, we're interested in both the classification and distinguishing ID versus OOD. So that's the setup here. So a common baseline is to use the softmax confidence score, which is also the largest posterior probability. However, it doesn't really work well because neural networks tend to produce this overconfident predictions, as we saw earlier. And so in particular, as highlighted in this red circle here, right? So you can see for both in distribution, in this case, cipher10 and OOD, there is a non-trivial portion of data that would have high maximum softmax probability, right? So in this case, you can't draw a threshold somewhere to, separate these two distributions effectively. And so in our NeurIPS 20 paper, we put forward an energy-based out-of-distribution detection framework, which has the core idea that influenced many of our recent works and other researchers as well. And compared to the confidence score, we show that energy score is better suited for estimating OOD uncertainty, both theoretically and empirically. And so here's this high-level view. Let's say we have this input X. It would go through this neural network parameterized by theta. And then we will derive this energy score, which I'll talk about the definition in the next slide. And then we perform this level set estimation based on this notion of energy. And here we flip the sign just to align with the convention that larger score is more indicates more IDness and vice versa. And so how do we define this notion of energy? So to explain this, I would like to draw a connection to how softmax is defined. So recall that this is the definition of softmax function, right, which is the posterior view of y conditioned on this input X. And so you can rewrite this to be this joint probability P of X comma Y divided by this likelihood term P of X, right? And so energy is really defined to be the negative log of this denominator in our softmax function. And so as you can see here, as the green box shows, energy has this inherent connection to the log likelihood. Even though they're not exactly equivalent, but I want to kind of, show this connection up front. And this is something we'll be capitalizing on later in this talk. And so with energy score, we see that the distribution become much more separable, and in particular, the in distribution in purple no longer have the spiky distribution that concentrates, heavily around 1. And to evaluate and compare the two approach, we train a model on cipher10 as in distribution and evaluate on SVHN as out of distribution. And here we measure the performance in terms of FPR 95, which is the fraction of OOD that's misclassified as ID when 95% of ID data is correctly classified or above the threshold. So in other words, lower FPR is better. And when we perform this separation using softmax score, we observe this FPR 95 around 48%. And in contrast, the right-hand side shows using energy score can effectively reduce the FPR by more than 13%, which is significant. And we tested thoroughly on more OOD datasets and consistently observe a significant improvement. And here the blue bars are based on the softmax score, and the green bars are based on our energy score. And so again, the model is trained on Cypher 10 and evaluated against 6 different data sets. And I won't go into details here, but in the paper, we also provide some theoretical insights for why softmax score is suboptimal for OOD detection. In particular, we can analyze the training dynamics of neural networks in terms of how they change the energy state of the output. And so, for example, we can derive the gradient of the loss with respect to the parameters theta. You can skip the derivation, but what I want to highlight is that the training dynamics essentially push down the energy for our training data. And so now if we look at the softmax score, or more precisely, the log of the softmax, it can be decomposed into the summation of 2 terms, as highlighted here. The energy score plus the maximum logit. And because the first term is going to be lower for our in-distribution data, and the second term is going to be higher. And so this overall summation results in a biased function that's no longer suitable for OOD detection. And I would also like to use maybe the remainder time sharing some of the research opportunities and outlook. And so far we have shown some measurement in terms of OOD uncertainty, but a question left in mystery is why neural networks produce overconfident output on OOD data. And answering this question requires us to carefully examine these internal mechanisms by which the network is trained and evaluated. And in our NeurIPS paper last year, we provided some insights on the plausible cause and mitigation of overconfidence issue. And this is joint work with my PhD student, Eo Sun, and my collaborator, Chuan from Facebook AI Research. And to explain the cause, let's look into how batch normalization, which is a widely used technique in training modern neural networks. And to recap how batch norm works, during training time, the network would estimate the running mean and variance for each of this unit based on our training data or ID data. And then during inference time, the network would then apply the batch norm statistics, which helps normalize the activations for the test data. And so everything works fine if you were going to test, apply the batch norm statistics on, the same IID data. However, our key insight here is that using mismatched batch norm statistics that are estimated on the ID data, but blindly applied to the OOD data, can trigger abnormally high unit activations and consequently model output. And so to see this, we can examine this activation pattern of the neural network. And this figure shows the distribution of activations in the penultimate layer of a ResNet trained on ImageNet. And here, each point in the x-axis corresponds to a single unit. And for each unit, the mean and standard deviations are estimated on this entire ImageNet training data, which is shown by the solid line and the shade. And then we can look at how, on average, how each unit responds to the OOD data for a naturalist, right? These images do not belong to any ImageNet categories. And so here we can again plot the mean and standard deviation in gray. And so if we put them together and contrast this activation pattern between the 2 types of data, we see that the activation for ID is well behaved with a near constant mean and standard deviation. However, for OOD data in gray, this mean activation has significantly larger variations across units and is biased towards having this sharp positive value. And it turns out such high unit activation can undesirably manifest in the output and causing overconfident predictions on OOD data. And so our observation on unit activation inspires this method called rectified activation, or REACT, which is surprisingly simple and effective. So the key idea is to perform post-hoc truncation to the unit activation at a certain threshold C. And so this can be done on any given model without modification to the training process. And this operation is applied element-wise, right, to this feature vector h of x. And a higher C indicates a larger threshold of activation truncation and vice versa. And then after the truncation, we can derive this model output, f react, by multiplying with this fully connected layer. And then finally, during test time, REACT can be leveraged by a variety of downstream OOD scoring functions S that depends on its f of REACT. And again, a sample with smaller score is classified as OOD and vice versa. And so in this slide, we show that REACT is quite flexible and is compatible with multiple OOD scoring functions, such as softmax score and energy score that we have introduced earlier. And in particular, we see that by incorporating this REACT operation, this OOD performance on ImageNet can be substantially improved. And so far, I have talked quite a bit about post-hoc methods. However, in my opinion, they're insufficient to fundamentally mitigate this problem. And in my view, mitigating this OOD risk really requires us to rethink how we design machine learning algorithms. And to explain what I mean, let's revisit this example. So this is a model trained using ERM on the in-distribution data. And so the decision boundary, right, is pretty good for classification, but they're problematic for OOD detection purpose. And going beyond ERM, we need training time regularization to explicitly account for uncertainty outside the ID data, right? So the ideal decision boundary should be something like the right-hand side, which is more aligned with the data density, and that's more compactly surrounding our data distribution. And so the question is really, how do we go from the left to the right-hand side without actually performing density estimation, right? Because estimating P of X can be quite intractable in high-dimensional space. And to do so, we advocate this do objective in learning, which is a combination of standard cross-entropy loss, which minimizes the risk on the ID data. And additionally, we have this uncertainty regularization term that tries to separate between ID versus OOD data. And so now let's zoom into this second term, which is more interesting. And so now let's assume we have access to some auxiliary outlier data. And here our key idea is to explicitly push the energy score to be a part between ID and OOD data. And so this objective has some nice mathematical interpretation too. Essentially, we're performing a level set estimation based on this measurement called energy that is related to the log likelihood. And the nice thing here is we don't necessarily have to estimate this P of X exactly for each of the data points, because all we care about is this level set. And so the result of the training is more separable distribution measured by energy score on the right-hand side. And so you can see that the FPR can be further reduced down to 1% in this case. So this is all promising, but this framework also has some caveat because it requires us to have some auxiliary outlier training data available, right? And so a question this opens up is, where do we even get those data from? And in practice, collecting a large outlier data can be arguably expensive. And moreover, this manual data collection and cleaning needs to be repeated for different ID data sets as well, which can be inflexible. And so we asked this question, is there any way we can generate OOD data automatically for free? And we answered this question in our iClear paper this year called Virtual Outlier Census, or VOS. Well, one natural idea is to adopt this GAN-based generative models for image generation. It can be intractable to synthesize images in the high-dimensional pixel space. And so our key idea is to estimate this class conditional distribution in the feature space rather than pixel space, and then sample outliers from this low likelihood region of the ID class. And this suits our purpose because we care more about regularizing the model's decision boundary, but not necessarily what the data points look like. And for example, the 3 clusters corresponds to 3 classes in the embedding space, and the dark points are the synthesized outliers. And so here's the big picture of our learning framework. It is a general framework that is suitable for both object detection and image classification. And so taking object detection as an example, we have this classification loss and the regularization loss as usual. But on top of that, we introduce this L uncertainty loss, which tries to separate between our ID embeddings versus the synthesized outliers in the feature space. And then during test time, we can rely on the output of this uncertainty branch to perform OOD detection. And to give you some real example, here I'm showing you the visualization based on a model trained on Pascal VOC. So for convenience, I'm also listing the training categories here. So the left-hand side is based on the vanilla FastR CNN without VOS. And so it misclassifies this road sign as a train. And on the right-hand side is when we introduce VOS to the training process, and it successfully identifies this to be OOD. And here's another example where we show that this stormtrooper can be successfully detected with VOS on the right-hand side. And again, this is with respect to a model trained on the DDD dataset. And our work is open sourced. Here is the GitHub link if you're interested in building further on top of this. So I think I have a few minutes left. And this work also leads to my next point, which is the need for a more realistic data model, right? When the field kind of started several years ago, a lot of the evaluation has been primarily based on the Cypher benchmark, which is great because it allows us to, it serves as a great starting point that allows us to make progress towards this problem. However, we should also acknowledge the limitation too, right? For example, this data set has relatively low resolution images, and they might not be reflective of the visual complexity observed in the real world. And so in the real world, images will come from much larger semantic space with much higher resolution, right? And so an interesting research question is to explore, ask, can we actually do OOD detection for ImageNet? And it turns out this problem is not as easy as we thought. And the OOD detection performance can decrease quite rapidly as with the number of classes increase. And this is because the decision boundary between our in-distribution data and the OOD data becomes a lot more complex, right? As you can imagine, as we add more data points and classes. And so one of the paper we published at CVPR in 2021 developed this group-based OOD detection framework. I think this problem is perhaps more interesting than the solution here. And so you can see that the blue curve is our method, which scales more effectively, right, as the number of classes increase. Whereas the gray line is the baseline that scales less so. And as part of the paper, we also released this new benchmark based on ImageNet. And here's the link if you're interested in checking out and creating even better solutions. I still think, there's a lot can be done in terms of, solving this problem algorithmically. And so definitely check this out. And this one last challenge, maybe I'll keep this short here. I also think as a community, there is a strong need for us to think about how we can better formalize this notion of OOD. In particular, data distribution in the real world can happen in many subtle ways. And to give you a concrete example, here we have our training data that contains some spurious correlation, For example, the bird species, water bird, land bird, is correlated with this background environment, right? Water versus land. And so the data generation process can be modeled by a combination of invariant feature that depends on the label Y, and also the environmental feature, which depends on, this environment, right? The background. And so it has been shown that the model can exploit such sparse correlation between the water background and this label water word for prediction. And so it turns out when a model relies on such sparse correlation, it can produce a high confident prediction for this OOD that has a similar environmental feature, right? Such as the water background, but a different semantic, such as a boat in this case. And we call this type of OOD sparse OOD, which is much harder to be captured compared to this conventional notion of OOD samples. And so what I want to point out is that it's very important to explicitly model this data shift by taking into account both the invariant feature and environmental feature when it comes to formulating this problem. And with that, I would like to conclude this talk. And thank you for listening. And if you have any further question, feel free to reach out, and I'd be happy to, answer those further.